So my name is Sundip Parikh. I'm a senior solutions architect at MongoDB. I spend most of my time working with partners and other ecosystem technologies, making sure they integrate well with MongoDB, or in the case of things like Amazon, make sure there's enough reference architecture, best practices stuff, so that if you're going to run on AWS, here's how you go do it. We've got the same things for Google Cloud or for other cloud providers, for storage with flash storage arrays. So got a lot of that kind of stuff. That's pretty much where I spend a lot of my time right now. I also still do training and consulting with customers and in the community as well. So I'll give talks here, do talks at MongoDB days that we have around the country. And then I think we actually have some training upcoming this fall in Austin, which I don't have the link for, but I can send it to you or I can post it on the mailing list if you guys are interested in training. I think there's a 2-day ops class and a 3-day essentials class. And we basically have 2 days of developer training or 2 days of ops training, or a combined 3-day class because there's enough overlap. So I think we're doing ops and the combined version this fall. So I'll send that out in case people are interested, because I think there's usually a discount code, and we can, if there isn't one, we can get you guys one for being part of the mug, at least get a little bit of discount on the training. But those are really nice because it's usually with people like me or other consultants who have done this and they've seen kind of the pitfall. So we've got the training manual, but we're also kind of answering ad hoc schema design questions. So it's a good place to bring your problem, and if it's not something we capture during the training, any one of us will happily sit with you during lunch or after the class is over, talk through it. So you'll get as much help as we can provide. But with that, why don't I get started? So what I want to talk about today is MongoDB and Hadoop. I know there's a kind of a cheesy business insights title here, but it really is how do you put these two things together? They don't compete. They're very complementary, but it's not always obvious in what ways they're complementary. Which use cases does it make sense to put the two together? So there's some of that to figure out. And then I want to walk through a little bit of so not just the actual how the two fit together, but some use cases that we've seen customers use for these two things together. What are the components that are at play when you're talking about Hadoop and MongoDB together? Which things work together? And talk a little bit about how the connector works. So actually how you physically connect these two things up in a real life environment. I've got a little demo that I want to run, and then I'll obviously take questions. At any point, feel free to interrupt me. And actually, I'm going to jump out of my slides really quickly and start my little job in the background, because it does take 15 to 20 minutes to run. So let's just hope that it works. Oops, not that one. Let me just check one more thing. Ignore what you're seeing. All right, that looks good. Okay, Hadoop is running fine, so we should be good to go. And run. All right, that should start spewing some stuff. All right, so let's, okay. Oops. Sorry, I've got some host name connection type problems from on a different network. All right, well, we'll have to come back to that, but let me start with this. All right, so kind of a brief, all right, what is Hadoop? Hadoop is a gigantic ball of wax, right? It's a lot of things to a lot of people. It's like the kitchen sink. It does all these great, powerful, crazy analytics, but at its core, it's really a set of components. It's a set of frameworks so that you can run, compute, and a lot of other things at scale. If you think about where MongoDB kind of falls in the size scale, it's MongoDB is great for gigabytes and terabytes at the sort of high end. Hadoop really takes it from terabytes at the low end to petabytes, and even I've seen an exabyte Hadoop deployment. So they are out there, they're possible. But that's where it's sort of, if you're trying to think about sort of the scale of the problem you're trying to solve, that's usually where the two fall. There's definitely room for a gigabyte size Hadoop problem. It's just, you have to balance out the cost of running the infrastructure versus just doing the work sort of ad hoc or sort of brute force in some ways. But people typically end up using Hadoop for a couple of main things. One is data warehousing, where they use it as kind of a central data warehouse for all of their data sources, whether it's SQL, SQL Server, Oracle, any relational thing, Cassandra, MongoDB, right? All these things can feed into Hadoop. So they'll use it as a broad data warehouse to connect all their information together. And then they often use it to do advanced analytics. So you can think of maybe you run part of your shopping cart mechanism on top of MongoDB, but maybe you have customer logins and other product metadata from other places. You could do individual analytics in each of those systems, but if you really want to get a total broad view of the entire company or the entire organization, you might need something like Hadoop. But it is, it's very powerful, but it is not for the faint of heart. I often tell people, like, you don't really ever configure Hadoop. You sort of just cajole it and you ask it nicely to try to do things for you. That's what it feels like sometimes. If you look at like the typical like enterprise IT kind of stack, focus, forget everything else, just focus on like the data management part. There's really two kinds of data, ultimately. There's operational data, and that's what feeds your applications. That's what your customers ultimately interact with, or your mobile devices, or what have you. And then there's the analytical side. And that's where you do like the data warehousing, or like the really powerful, broad analytics, right? But the two really do need each other. You can't have operational by itself. You can't have just the analytical, right? Operational feeds the analytical side, and the analytical is supposed to feed the operational side back. So if you take like a usual, retail example again, with recommendations, you have to get the recommendation data in from somewhere. You have to get ratings and comments and reviews in from the operational side, but you actually do predictions and predictive analytics or customer churn on the analytical side. But then you have to feed that back in to the end customer, right? You want to show them movies they might like or products they might be recommended by other users. And that's how you put those two things together. So they have to kind of feed each other regularly to be effective. I think a lot of like Hadoop companies like Cloudera and Hortonworks and Matt Barr talk about like the enterprise data hub or the enterprise data lake, all this, whatever jargon they use. Ultimately, you need like a river or a tributary into that data lake. And so operational data is what that is, right? That's what's feeding all those big, powerful analytics, because that data's got to come from somewhere. If you take nothing away from what I'm going to talk about today, the key word to remember is enrichment. And it kind of goes back to what I'm talking about. Applications and interactions, right? All that stuff that powers your apps or your mobile apps, your web apps, SaaS software, what have you, all that lives in the operational side, but the warehousing and the analytics have to come from somewhere. So you do need these things to really work in concert to be effective. And that's how you develop, the right way to kind of run your business off this stuff. If you look at the typical use cases for MongoDB, these are things that we see a lot of with customers. It's kind of an endless list, but this is the stuff that we feel like gets surfaced the most. So we see a lot of like first level analytics use cases. So MongoDB's got a really powerful built-in aggregation framework. So if you want to do like basic summing, counting, averaging, grouping, that stuff's great to do in MongoDB. And it's like first level reporting. It's great on that one data set, but it's not across the entire thing. But that's one thing. Product asset catalogs, like for retail, for example. We see a lot of uses in security and fraud for like managing customer logins or transactions that are happening across a large system. Internet of Things, which you could call that any number of different terms, but time series data is often used for Internet of Things. Basically, think of any sensor that has to report and record data. We're a great fit for that as well, since we can take that data in easily and you can model it in any number of ways. Obviously, mobile applications, customer accounts. Single view the customer is really popular. It's kind of like, the one example we always use is with MetLife, right? Big insurance carrier. They have insurance policies. You may have like 5 or 6 insurance policies with MetLife. Up until about a year ago or 6 to 8 months ago, they didn't have a way for you to call in one customer support number, and that customer service agent couldn't see all of your policies in one place. They actually built a solution for that purpose on MongoDB. So now they have one customer record, and it's got every policy and all the associated policy metadata. And it's not the sexiest application in the world, but it's actually something that a $1 billion business didn't even have. And so they were able to build that on MongoDB. After like a failed effort of like 3 years, I think, or 2 or 3 years on relational, they built it on MongoDB in about, I think, 3 months, right? So they were able to get to production very quickly with something that was able to scale.
8 to 9 days.
Yeah, 89 days, there you go. Yeah,
beta in 9 days.
Oh, beta in 9 days, wow, okay, so. Social, again, is another one. If you guys have ever used Foursquare, that's a big social application built on MongoDB. That's primarily for geospatial, but it is also a good fit for a lot of other social applications that we see. On the Hadoop side, you'll see things like, broad churn analysis or like powerful recommender systems. Obviously, data warehousing and ETL we talked about. We're seeing a lot of interest in financial services for doing like big risk predictions on like, assets that get traded. It's all stuff I really don't understand. But trade surveillance is another one that comes out of financial services. Predictive analytics, right? This is a lot of what like is Hadoop's bread and butter, right? Big, powerful analytics that you can do across, again, terabytes of data or petabytes of data. Ad targeting, sentiment analysis is another one where you can analyze a lot of language. Yeah.
How about financial models like profitability analysis?
I think a lot of it's fair game, and a lot of it comes down to like the scale with which they're trying to run. And it's not just the scale to compute, because it's always been possible, right? You just get a bigger and bigger machine to do that stuff. What they're seeing, part of the reason we're seeing a lot more of Hadoop lately is because it seems to be cheaper to scale and add more infrastructure, more compute, and they're able, like a lot of the tools that weren't there with Hadoop like 2 years ago are starting to show up. So a lot more like business intelligence software talks to Hadoop. There's a lot more like SQL access on Hadoop that you can do. So a lot of people that didn't have Hadoop knowledge can now do SQL across petabytes very easily. So I think a lot of those use cases are fair game if they're big enough. There's probably a size trade-off there between the amount of time and effort it takes to run a large Hadoop cluster versus what you have to actually analyze. But it's a sliding scale, and I think it just depends on how you run it.
Yeah, quick question. So going back to the single view of the customer,
Yep.
you had mentioned about not having native support for joins. So did you guys implement it with embedded documents? Or?
Yeah, so that's a good example. So yeah, I wish I had an example to show you, but that's a good question. So the way they did it was there's sort of a base customer record, and then there's separate kind of embedded, it's actually an embedded array of just documents that span the actual individual policies. So each of those policies has different metadata, like start dates and end dates, dependents or not, depending on whether it's like life insurance or medical insurance, that kind of thing. How that actually works is they've actually got a large ETL layer at their company. I don't remember if they use Informatica or something else, but they have a broad ETL mechanism. So that basically every day is ETLing more and more data from like 10 different source systems into one cohesive MongoDB document per customer. And they had to do a lot of work to like data cleansing along the way because they had a lot of mismatches across the board, but generally that's how they're working on it right now. So if you put together these two things together, and I don't know if this arrow's showing up, but this is the enrichment arrow that I like to call, right? These things have to feed each other. You can't do recommendations or predictive analytics without the actual product catalog. And I know I kind of hit on this repeatedly, but again, enrichment, that's the key word to take away from this. So what are some of the use cases we've seen? So I couldn't share any customer names specifically, but commerce, again, is a good example. This is a major retailer. So they do products and inventory. They showcase their recommended products based on their analytics through MongoDB customer profiles, and they manage individual user sessions. And then on the Hadoop side, they come up with elastic pricing models, right? Because every time you go and look at something, whether it's in your sort of saved wish list or not, they might bump the price by a few cents, or they might drop it a few cents to get you to buy. So they compute a lot of their elastic pricing models that way. Obviously recommendations, predictive analytics, and they do a lot of clickstream analysis too to see how traffic flows through their retail site. And right, they're using that to figure out ultimately things like customer churn, if you will. Insurance is another one. So insurance is kind of, I pulled this from the MetLife case, but they've got customer profiles, insurance policies, they get customer session data from their web applications, and they're actually incorporating, in some cases, call center data. So call center IVR systems that capture call interactions, that stuff is actually a pretty good fit for MongoDB, and they can pump that into Hadoop and then start figuring out why they're losing customers, right? This is a pretty critical business thing. So it's very technology centric, but ultimately it's feeding a business concern, right? Why are people leaving our site? Why are they leaving us as a company, as a policyholder? Where are they going? Could we have caught that at some point earlier on in their life cycle? That's the kind of stuff they're trying to work on. Yep.
You see a lot of companies now just kind of dumping data and figuring out later how they might data mine it?
Yeah, a lot of times. A lot of times people will just say, well, let's put everything, you go in, depending on who you talk to, they'll say, well, let's just put all Hadoop and Hadoop will figure it out. And that's sort of the polar opposite of the way it works. You have to really understand what you're capturing, but they're spending a lot of time sifting, cleansing, and getting to a point where they can start analyzing.
You see a lot of log data in there?
Yeah, tons. In fact, part of the genesis of Hadoop was around log data specifically. So they were consuming application server logs and web server logs to figure some of this stuff out. And as they've added support for third-party data sources, like they're trying to incorporate all of it now.
Yeah, a lot of companies as they scale, they want to have a common sort of monitoring hubs. Is this what you see a lot of times being used to consolidate? Every application, the company has to send their stuff to this data bus, and it all ends up in some.
Yeah, a lot of it depends. I mean, you still have a lot of like really solid, application performance monitoring, like New Relic and App Dynamics. Like those guys still have their own infrastructure, but they're making their data available to things like Hadoop so it can be pulled in for bigger analysis. And again, to be combined with other parts of the data set they don't see.
Nice.
So that data is still becoming more useful. But even those guys like App Dynamics and New Relic, they're starting to add predictive models to their work as well, because they know they can start predicting sort of like, well, you're going to see a rise in your application's usage on a repeated pattern every Monday morning because that's when people shop the most, or what have you. So they're trying to leverage, everyone's trying to get smarter about it, because if you think about it, everything reports data now, right? I mean, my phone is reporting data right now as I stand here, doing nothing with it. It's sending data up somewhere about something, and they want to start using this stuff. So it's all out there for them to use, but they're trying to figure out how best to leverage it.
Right.
Fraud's another good use case, and we see this being really useful because it does have this kind of circular flow built into it where sort of payments come in, and maybe this part doesn't exist yet because there's no fraud modeling, but you get payments in, you pump them into Hadoop, every night there's kind of fraud modeling done with sort of third-party data sources, maybe parts from other parts of the company, you dump that out to a results cache, and then now, on day 2, when you start collecting payments, you can double check those against the fraud mechanism. So you start to see this way of like the give and take that you get when you put these two things together. This is a little bit more complex, and it does obviously involve sort of third-party data sources, like maybe known bad credit card transactions, or if someone's been recently hacked, they have to change that third-party data source. But some of that stuff is useful. Again, you feed the mechanism, and then once it starts rolling, you start incorporating what you've already learned, so you get better and faster at it. And now a fraudulent payment that comes through doesn't actually even get processed. It gets double checked by the fraud mechanism and then booted out before even charged, as opposed to sort of handled after the fact. And so that has a totally dramatic impact on how a business can run and charge their customers back. All right, so that's a little bit like a primer on the use cases. I want to talk about the components. Part of the Hadoop stack. This is a hilariously small subset of what's out there. Yeah.
So in some of your use cases, you talked about customer churn that people are using, like in insurance, telecommunications, media and entertainment. Wherever people have customers or subscribers, they are interested in customer churn. So my question is, when you are building a customer churn model, would that model be still the same? And it's just that you plug in the new data source for insurance or telecommunication, the same thing would work, or you'd have to build a new model for each industry?
Ultimately, what we're seeing is everyone's building individual models. And so that's part of the problem, is that there's a lot of canned analytics out there, but you either have to shape your data coming in, or you write an algorithm that takes advantage of all of your data sources. So it just depends. A lot of cases, what we'll see with like recommender systems is they'll cleanse their data coming in and try to simplify it down to like user, product, and rating, right? Something really basic. And then they'll keep updating and feeding that model again, so it gets better and better over time, and they'll persist the model so they can refresh it very easily. In other cases, they're writing something from the ground up because it's very tailored to their business. Ultimately, it depends on how much data you're trying to look at. Not the volume of it, but sort of the number of columns, the number of attributes you're trying to capture. Because some of the canned ones exist and they're very powerful, but they also make a lot of simplistic assumptions. So I think it's safe to say that most people are rolling their own in a lot of cases, because that's just the most effective way. Okay. So the Hadoop stack. So again, there's a lot of components I left off the slide. Part of that is because, one, the slide is only so big and there's so many pieces here that they wouldn't fit. But also, I wanted to focus a little bit on the parts of Hadoop that we are sort of trying to work best with. And so if you start at the very bottom, there's HDFS, and I'll go through all this in a little bit more depth, but HDFS is the storage layer. Yarn is kind of the compute layer, right? And then, the resource manager layer. And then you got MapReduce and Spark. Those are two popular compute options. And then on top of MapReduce, you've got some higher level abstractions like Pig or Hive, right? Those are the tools you can use to do sort of the same style of analytics you might do in MapReduce, but with a different language interface. So let me dig into those, or all those pieces. So HDFS is the Hadoop distributed file system, right? This is kind of the core of what you set up when you deploy a vanilla Hadoop cluster. You're basically putting a bunch of nodes together, and you're saying, all right, this is one giant bag of storage. And when you save files there, behind the scenes, it's actually splitting those files up into small pieces and spreading them around the cluster, using its own heuristics to doing that. Yarn is a layer that sits above it. So Yarn is the resource manager. And so back in the day, before Yarn, when you wrote a MapReduce job, you would basically be taking over an entire cluster. So if you had a 10-node cluster, it would run across all 10 nodes. If you had a 1,000-node cluster, again, it would run across all 1,000. Now with Yarn, what happens when you submit a MapReduce job, you actually have the ability to elect how much you want to use for different phases. You might say, I've got a 1,000-node cluster, but you only ask Yarn for 10 mappers and 10 reducers. So you kind of get a sense for how to actually manage your resources effectively. And this is, I would say Yarn is probably one of the biggest shifts, because it's taken Hadoop from being, I think, segregated like a labs style deployment where it's very small and very targeted cluster to now an organization can run one giant cluster and now segment off resources dedicated. So they could say your team only gets 10 nodes, your team gets 10 nodes, and Yarn lets you manage that stuff and actually dole out resources. So you can basically get more efficiency out of your entire cluster. But it's really the way you interact and how you schedule things. It's if you want to think about it. And I think actually Yarn stands for yet another resource negotiator. So it's really just there to kind of govern, control. MapReduce is a popular paradigm that Google wrote a paper about years ago. It's actually, I think, 11 or 12 years old at this point, so it's pretty old. But this is how you do sort of the basic computation across a Hadoop cluster. MapReduce is not specific to Hadoop, it's a general programming paradigm. But here, specifically, this is how compute was initially done with Hadoop. MapReduce is really powerful, but it's also very, very, very limiting, right? It's a very single-focused, task-centric API or model. So if you have a very complex problem, like a linear regression that you want to do across a petabyte, you can't just do a linear regression in MapReduce. You actually have to take that sort of work and parcel out into individual MapReduce jobs, and then run that entire thing as like a super workflow. So it's powerful, but it's also very limited. So it does introduce a lot of overhead and work to really take a complex algorithm and break it into these small, tiny tasks. Because each MapReduce phase can run across the data set. But if you need to go back over and over again to like converge on a solution, that's just more MapReduce jobs. And you have to take sort of the output from one reduce and make it the input to the next map. And by the way, all this time you're like reading off of HDFS, writing back to HDFS, reading back from the storage. So it adds a lot of I/O overhead too. Again, very powerful, but not anything approaching real time, I would say, and much more batch oriented if you're thinking about that sort of like old school way of doing things. Like I said, it's powerful, but sort of limited in the scope in which it can do in a single job. So you have to wire these things together. With Pig, you get kind of a higher level abstraction on top of Hadoop. So Pig is like it's got its own language called Pig Latin, and it's got its own operations, and this is a subset of them. It's like load data sets, filter data by some attribute or field, join different data sets, group them together, and then do some kind of aggregation like summing or counting, gets you iterate across different result sets, and then store them back out. So this is pretty much how Pig works. It's a different language entirely, and it's a level up from MapReduce. But a typical Pig script that's like 10 lines can end up being like 5 or 10 MapReduce jobs. So it does abstract away a lot of the busy work and overhead. You lose a little bit of flexibility, right? In MapReduce, you're basically limited by the Java API. So anything you can do in Java, you can technically do in MapReduce, given the right algorithm approach or algorithmic approach. Pig is a little bit more limited in its core language, but Pig does support user-defined functions. So if you have some weird custom transformation you want to create, you can just write a Java UDF for it, compile it, and it becomes a Pig module you can just call in your code. So you still get a lot of the same power, but generally a higher level of abstraction. And we see Pig being really popular with not big data engineers like in the classic sense, but like just, a regular developer can figure out how Pig works and write a Pig script, and it still gives you all the same power of the entire cluster, just with an abstraction that's much easier to read and follow, and ultimately to kind of manage through.
Yeah. Is this like the T in ETL, transforming, trying to?
It's a little bit of both. Like you can actually you can use Pig for like big ETL jobs. It just takes a complex script. But again, it's a question of, do I want to do that ETL job in like 30 MapReduce jobs or one Pig script? Because a Pig script can be really complicated, but it can still be one script. I mean, I've seen a Pig script easily like do the same work that like 10 jobs could do, and you don't have to worry about the workflow part because it's handled for you.
Right, but the data is all unstructured. It's eventually this thing.
Yeah, this is going to extract it and then
right,
exactly,
right.
yeah.
But
do some transform, but it could do all the steps in the ETL process. So anything that Hadoop can talk to, Pig can talk to by virtue of it running on the same infrastructure. Hive is sort of similar. Hive is intended to be kind of a bigger data warehouse infrastructure on top of Hadoop, but instead of having its own language, it uses a subset of SQL called HiveQL. So now imagine like every business analyst out there that knows SQL can suddenly sit at a console and run 30 MapReduce jobs without ever touching a line of Java code because it's basically SQL, right? And it's a pretty fair subset of SQL. It's not kind of a neutered group, right? It's a lot of the same things you can do with SQL are represented pretty well in Hive. And if you look at the trend of where a lot of investment in Hadoop is happening, if you look at Cloudera, Hortonworks, and all these other companies, they're really pushing hard on trying to make Hive better, faster, and more powerful. Hive has historically been kind of slow because it's always run through the regular MapReduce mechanism. But now what you're seeing is like, Cloudera's got their own offshoot called Impala. Impala has its own file format. It doesn't go through MapReduce, but it's a shit ton faster, right? Hortonworks basically spent the last like year making Hive like 100 times faster, because there's a lot of different ways they can optimize the execution if they cut loose some of the old parts of MapReduce and just focus on building a better execution engine. Because once you can give people SQL access to their data, it becomes fundamentally more powerful. And now all these other like business intelligence tools, reporting, visualization, all those things already talk SQL. They already speak that same language, so you can plug them right into Hadoop now and start doing the same visualizations and analytics that are canned, but in your typical reporting tool. So it's kind of opened up a lot of interesting functionality. And again, if you look at where it was making investment, a lot of it's on SQL on Hadoop solutions. But it does have the same kind of cool parts about Pig in that whatever you can't do in there, if there's something you find you can't figure out, write a UDF for it, compile it, and it becomes another function you can call inside of Hive. So it still gives you a pretty large doorway to kind of work through. The last one I want to talk about is Spark. So think of Spark as sort of the idea of MapReduce like this compute layer, but evolved by multiple generations. Spark doesn't require you to take your problem and make it a MapReduce problem. It lets you just write regular code in one big file if you want to, but you get all these built-in transformations and actions in your data set you didn't have before. So for example, a two-class MapReduce program in Java is basically 2 lines in Spark, right? It's you call map and then you call reduce, and it does it all in line. You don't have to worry about the I/O transition between them because it actually tries to leverage as much memory as humanly possible. You actually have control over serialization. So if you want to have a custom serializer for objects between phases, if you want to have like different parts of it write, or run different functions across an entire data set, you can do that. Spark is really powerful. And people are just scratching the surface. It's really new, right? It's a lot less mature than the rest of the Hadoop ecosystem is, which itself is not terribly mature. It's only been like 5 or 8 years. But there's so much promise that like Cloudera and Hortonworks specifically actually said their next generation SQL on Hadoop solution is going to be powered by Spark. The Hadoop machine learning library, Mahout, was previously built on MapReduce. They're abandoning all their code now, except for like a small portion of it, and moving all the way over to Spark. So their next major release is going to be all running on Spark, because Spark's model is much better. And it's not that MapReduce is bad, it's that everyone had to do MapReduce first and kind of learn the lessons and see how people use these things. And now they've kind of taken all that data and they said, all right, well, we can build a better algorithm. And so they came up with Spark. And so Spark is actually a project out of the UC Berkeley AMP lab, the machine learning lab there. They spun it out and it's now a full Apache project. And it's very well supported, and they're making a lot of progress really fast. And they've got a ton of really canned, powerful things. Like Spark, just the basic compute framework is there. There's a graph mechanism, there's a SQL mechanism, there's a streaming mechanism that's kind of similar to Storm. They've got machine learning with their MLlib, and I think they're also working on now interaction between, or a connection between R and Spark. So instead of, you run like your really complex algorithms in R locally, then you just push into a Spark job and it runs it across the, the petabyte data set. So let's talk about the connector that actually enables all this stuff to move back and forth. So the MongoDB connector for Hadoop has sort of 3 main areas. So the data it operates on is data that lives in MongoDB, whether it's a running deployment or in BSON backup files. So if you run like Mongo dump at your console, you get a dump of like BSON files. That's our native file format. And you can leave those in HDFS or S3 or wherever you want to. And then the connector can read from those files and pull them in. It can also read from, like I said, a running MongoDB deployment, whether it's a sharded cluster or a replica set. It actually does a good job of like honoring read preferences. You can read from things like secondaries. You can read by chunk or by shard. So you get a lot of flexibility with the connector. And then it enables support for MapReduce at its core, Pig and Hive as well. And then the Spark support is through the MapReduce API right now, but we're actually looking at how to make that a little bit faster because the MapReduce API is sort of limited by its own nature. On the platform side, it supports, obviously we support Apache Hadoop, Cloudera CDH5, which is the latest release, or I think 5.1 maybe. And then Hortonworks HDP 2.1 is what it's certified against. And it also works on Elastic MapReduce. So you really do have your choice of them. We haven't actually tested MapR's M6 in quite a while, but it's supposed to work. And it's on my list of things to do at some point this month. So, or not this month, it's almost done in September. So yeah, I covered that. So it talks about MongoDB and BSON. We have input and output formats for MapReduce jobs, if you guys have looked at MapReduce before. And so the connector will actually go and say, all right, well, you've got like a terabyte data set. I know how to split that thing up into small pieces, so I can assign each mapper in your MapReduce job to pull in pieces in parallel. So we try to do the right thing to make sure it's as concurrent as possible. We're not trying to force, a terabyte through a tiny little hose. We're trying to give you as much parallelism and concurrency as possible when you're reading this data in. And then you could actually also, if you're running against a live MongoDB deployment, you can filter incoming data. So let's say you only want to read, like, maybe on Monday you read the entire collection that was a terabyte. Next Monday you only want to read the last, few gigs that came in over the week. As long as you've got a datetime field in there, you can filter that data down or filter by some other attribute.
Yeah, I was just gonna say context on the connector. So this is like your first slide was you had operational. And
yeah, this is
pulling data to the.
Yeah, so this is what's giving you bidirectional access between Hadoop and MongoDB. Yeah. No, thanks for asking that. It supports authentication. So if you're running with security on MongoDB, you can authenticate correctly. You can read directly from a sharded cluster, whether you want to go through like MongoS, the router, if you want to read from shard primaries, or if you want to read from replica sets or replica set tags, that's in there. So basically all of the MongoDB connection string format is totally supported here. So you can get very particular about where you go. And so if you think about a big sharded cluster, I can draw it on the board for you, but I don't see a marker. But if you have a big sharded cluster,
Around the corner.
oh, thank you. So in like a sharded cluster, right, you've got sort of your application up here, and your app is running MongoS, like the query router, but then you've got individual shards across. Right, this is a big shard cluster, and I have terrible drawing skills. But you've got primary, secondary all the way across. You can actually control where your data comes from with the connector. So if you want to say go through MongoS for everything, that's fine. If you want to go and read directly from shard primaries, you can do that. If you want to read from shard secondaries, you can do that as well. You can basically do it in a way that reduces as much load on the operational system as you want to. Because ultimately, your application or applications are still running and writing and reading here. You don't want to negatively impact them, so you want to pull the data from where it's least impactful. Yeah.
So when you talk about pulling the data, excuse me, are you actually talking about something that pumps data from there into a Hadoop cluster? Or are you talking about a Hadoop job that queries the stuff that's actually in MongoDB?
The latter, yeah. So you've got a Hadoop cluster over here running a job. That's a small cluster, but you've got a Hadoop job. So it's actually pulling data and reading it in here and pulling it out.
But it's part of his job. You're not like batch loading and then doing analytics in the Hadoop, right?
You could do it both ways, but yeah.
But that'd be a data dump.
Exactly. And then you're not getting real-time data. And I can actually talk a little bit about that a little bit later on. So we'll actually cover that exact use case. And so the nice thing too is when you're writing that data back out, right? You're writing analytics back out to MongoDB. However you do that, you can either write it out to a brand new collection or you can update an existing collection. So again, if doing things like recommendations, you're not going to compute these things one time and live with them forever. You're probably going to recompute recommendations on a regular basis because people are adding more ratings or more reviews. So you want to pump this stuff back in. So instead of having to write to a whole new collection every time, you can actually update the existing records and say, well, the 5 movies you liked last week are no longer valid for you. Here's 5 new movies, and put them in that record. So you get a lot of flexibility on that.
Okay. So getting back to that, with MedLive from a single view, the patient or the customer's policy. So you had an ETL updating the person's office policy. So is there any, do you do any locking while that's being updated?
Yeah. So in their case, they took like an online offline approach to it because they couldn't do it in real time. Like it was too impactful in too many places. Okay. So they would take like nightly dumps. And they're actually doing this on a I think daily or weekly basis, or they were up to that point. They would take like nightly, they would pull in all their data from all their source systems nightly, compute the customer records from that, and then push them out that day. And so new updates to customer information are still going to the old system as of about 6 months ago. So they were still writing to the old data sources, but then creating the read records that they would use to drive customer service from that ETL job. So every day they're basically refreshing all the customer data based on what's come in from the previous day. Now the plan, last I looked at it, was to start taking writes in from that customer data on the MongoDB side and then pushing that back out. So they're trying to get to a point where they can go bidirectional with that data, but they have serious scale problems because they have a lot of data and they have a lot of things touching the data all the time. So they fixed the customer service part of the problem by making this application, but they've still got to fix like a lot of the other original policy holding mechanisms. Yeah.
So when you're talking about the MongoDB connector, are you talking about something similar to Scoop?
Yeah, it's similar in principle to Scoop. Scoop is like the connector you can use for a sort of typical relational databases. It works in a similar way, except it's not driven by like a central console. With Scoop, you're basically saying, all right, go pull this data in and put it in HDFS, and then I'll process it later. Or you might feed a MapReduce job from a Scoop job. In this case, it's typically like a live thing where you're using the connector in your MapReduce code, and you're saying, go pull data from this data source and push it in. So in a lot of cases, if you think about it with Hadoop, you've got kind of, if this is like the MapReduce layer, you've got HDFS underneath here. In a lot of cases, we see people sort of bypassing HDFS and just pulling data straight into their MapReduce job. And they might write results here, but they also might write results back in. In some other cases, depending on how you want to manage the operational load, they're putting that data here first and then computing here back and forth.
So second one, looks like it's a bi-directional thing. So is there a size limit? How are you filtering that?
No, there is no size limit. It's pretty much limitless. I mean,
it's more like streaming, direct streaming, or?
Not regular. I mean, if you're doing if you run a MapReduce job that pulls data from MongoDB, it's going to pull all that data in that one fell swoop, and it's going to. I mean, the specifics how you run MapReduce jobs are a little wonky, but ultimately, you start a bunch of mappers, they all pull in their subset of data, and they start computing. So they're not waiting for all the data to come back in, they're waiting for their subset to come in before they start running through it.
From an architecture point of view, how do you, a lot of times applications have encapsulated database, and so how does this work with the connector in some ways, right? Because you're kind of going in there for the application coverage.
Right. So a lot of
best practice there.
Every organization handles their data differently. So a lot of times you basically have to have the developer that wrote this probably has to sit with the developer writing this because they've got to understand how the data is actually structured in some way.
Especially on the right side of things, right?
Yeah. So there's a lot more give and take. But with MongoDB in general, you tend to see that a lot. You might have had a separate dev and ops team in the past. More often than not, with MongoDB, you have to put those two things together a lot more. And the same is sort of true of big analytics here. You kind of have to know what the application is doing. It's not just a big pile of data. It's got some meaning to it. And you need someone who understands that meaning to help drive how you're going to analyze it. Otherwise,
especially on MongoDB, right?
Yeah. Right. It could be coming from anywhere. And there's a lot of things that we have to figure out still too, how do you redact fields on the way out? Maybe I don't want to send, I might have social security numbers here. Exactly. I don't want to send those over here because they don't need them for that. Right. So there's some of that still to work through as well. But yeah, that's a good question. All right, so if you're configuring a MapReduce job, if you guys have never done this before, this is going to look a little foreign to you, but ultimately, everything in Hadoop is still pretty XML driven. So you have to do things like create XML files that have this information in it, where you have to set these properties at runtime when you run a MapReduce job, and I'll show you an example of this. So, but basically, it gives you kind of a rundown of when you're specifying how the connector should work, you have to tell it where to actually get the data from, whether it's talking to a live cluster, whether it's writing out to a live cluster, or if it's using BSON input and output, which is that backup file format that we use. So a quick example of what a map job might look like. On the top, can you guys see that okay too, or is that reasonably readable? Okay. On the top, you've got, basically think of this as it's movies and genres. And what we want to do is just get a count across the data set of genres and the number of movies that correspond to the genre. So the map job basically takes in, it extends the normal mapper class, but you give it a BSON object, and I'm telling it the output is going to be the genre name and a count. And so inside the map job, I've got a BSON document, that's the MongoDB format. And all I'm doing is, because I've already filled out that configuration, when I run this job, it knows where to pull the data from, it pumps it through here, and it passes each document through the map phase. So every document is going to hit this loop and say, all right, well, for every genre, just write out the genre name and the number 1. Right? So it's almost like a word count example, where I'm just going to go through and say, all right, well, I saw action once, action once, action once, and then when you get to the reduce phase, what gets given to that is a list of action and all the numbers that it saw. So it's almost like doing a group by around genre. Obviously in SQL, this is 2 lines or 1 line. In Hadoop, it's a lot worse, but this is a trivial example because it fits on the slide. If you were doing this, right, again, this is terabyte, petabyte scale, so it's a lot more complex. But in the reduce job, it's basically the same thing. You're getting a list of, you're getting a genre name and then a list of values that correspond to that genre name. So all we're going to do here is we got the key and the values. We're just going to sum up all the values here and then write this out as a new document in MongoDB. So all we're going to do is output a document that says genre name and how many times I saw the genre go by in the movie data set. And so if you look at the output of MongoDB, it's basically just the genre name and the count, right? So this is a pretty simple example, but it shows you how to like talk to these documents. Once you get that document into a mapper, it's basically the Java API for MongoDB. You can do whatever you want there with the document. If you have a nested structure, if you have an array of complex things, you can go pull it apart, tease it apart, count it, emit it however you want to.
So
Yeah.
what I see from the code is basically you're providing that writable based on writable. Is that but someone has to actually code it up in Java?
No, this is, I mean, there's a little bit more code that I've left off here to actually run this job, but ultimately it's just this MapReduce class. So all the beside writable stuff, all that stuff is coming out of the connector. It's a class in the connector, so you're just importing that piece.
Right, but then this MapReduce job is someone actually coding.
Yeah, someone's writing this MapReduce job up, yeah. And so you can see like, this, I mean.
But yeah, it's pretty small.
Yeah, I mean, I like Java, but this is ridiculous, right? This is a lot of busy work to write all this stuff out for really just what amounts to a for loop or a group by, something pretty basic. So again, MapReduce is great because it's powerful that it can run across a lot of hardware, but for anything but the simplest tasks, you have to really fundamentally rethink how you're computing the answer to this question you're trying to ask, because it's not an elegant API in a lot of ways. Which is where Pig actually comes in. Pig would, if I did that in Pig, it would have been about probably 3 lines. 1 line to load the data, 1 line to do a group by, and then a 3rd line to output the data. So that just gives you a sense for how different, MapReduce and Pig are, because Pig is just so much more powerful abstraction above it. But with Pig, we give you the same things. We give you like a BSON loader for BSON files or a Mongo loader if you're going to read from a MongoDB cluster. You have the ability to pick and choose which fields you want or map them to particular Pig data types. On the insert side, we give you the same output mechanisms. And then we also have an update mechanism. So if you want to update existing collections or existing documents, you can do that from Pig as well. So all the same functionality that's in MapReduce is inside of Pig. If you get into the kind of the specifics of it, either you have to pick 1 or 2 schema approaches. Either you bring the entire document in, or you just bring a subset of it in. So that does have some impact on how much data you have to read in from the cluster. And then we will do some work in auto mapping some of the types, but embedded documents and arrays can get kind of complex because if you think about a MongoDB document, it can get pretty far nested before performance falls off. Like you can go 7 or 8 levels deep. When you start turning that into Pig maps and tuples, it can be kind of hard to visualize. So a lot of times you'll spend a few lines just deconstructing like some of those internals so you get to the structure you actually want to compute across. So it's a little bit of work to do that stuff, but you have to do it regardless if you're trying to break it up. And then you have to do things like supply an alias for the underscore ID field because that's not a valid Pig variable name. But it's actually pretty, I can even show you guys an example Pig script later on. Hive is actually even easier, right? With Hive, you don't actually physically bring in the data so much as you just create a table in Hive that maps to MongoDB collection. So you're just sort of creating a mapping between the two. And then after you execute this statement in your Hive query, you basically have the rest of SQL to do, or the rest of the Hive query language to do whatever you want. So if you want to do a filter, like if you want to use a where predicate, or you want to do a join or a group by across like 10 tables, that's fine. You can just use this table as a regular Hive table. So it kind of abstracts away all the work. And again, you have the same idea here where you can actually pick and choose the schema fields you want to be represented. You don't have to pull them all in if you don't want to. And then you specify things like the URI. So like if it's again running against a MongoDB cluster or just BSON files, you pick the appropriate storage handler. And so when you're writing data out, there's no output format in Hive. You really just create another table and then insert data into the table. And that's it. And as long as it uses the MongoDB storage handler, it knows how to handle input and output in that case.
So how do you handle nested hierarchy?
Here, I think the types, so like embedded documents become structs if they're single types, or mixed types. Single types become just a map, and then arrays are arrays and object structs. So you end up having, again, to do a little bit of like, you want to sit at the REPL or the console and like iterate through a few documents and see what they look like in Hive, because they sort of end up being like flattened, kind of, but you have to deconstruct them a little bit. So you might have a very complex struct that you have to go in and like decompose a little bit to work with it. So it's a little bit of work, but it's not as harsh as if you were to try to flatten it for like a relational use case. Like Hive does understand some higher level data types, so it is still pretty possible. But you end up having to like, if I were sitting here and doing this, like I end up creating like a table, I limit it to 5, and then I just output that 5, see what it looks like, and then try to write my query, is usually how I do it. Oh, go ahead.
Sorry, and then you touched on this on all three examples a little bit, and mentioned it before, but you're actually specifying like your source collection, and it's going to pull the data across the job, and you said every mapper can get a chunk.
Yeah.
Is it streaming a cursor, and then they're getting them linearly, or serially, or is it actually in parallel?
It's in parallel.
How does it? So the connector sizes it out and figures out the offsets.
Yeah. So for like a sharded cluster, I don't know how much you know about the internals of a sharded cluster, but basically like the connector will go and say, all right, well, it actually reads from a box I didn't draw here, but there's config servers over here that actually hold the metadata for a sharded cluster. It actually goes and reads the config servers first and says, all right, well, give me a shard by shard breakdown of where all the chunks live, and then it'll basically rewrite the query and say, well, I've got 10 mappers and I've got this data set. Give me 10 subsets that I can execute. Each mapper executes a subset of that query that pulls that data. Now they might all be running through the same MongoOS, so there's a little bit of a bottleneck there, but ultimately coming off the shards or from the chunks themselves, they're all parallelized. So you're getting, I wouldn't say 100% parallel performance or concurrency. You're probably getting like somewhere in like 2/3 of that.
Well, are you saying you're piggybacking on the fact that the shards distribute? What if you just have one single server? How does it note it?
Yeah, then it basically does. There's an internal command in MongoDB called split vector, and it basically says, well, how many splits do you want? And it'll go across the data set and give you. It doesn't give you. You can't do a source query in that case. You have to go by the splits it gives you. So it just says, all right, well, here's the total ID range. Just give me 10 subsets of the ID range, and it gives you back a min and max. And then the connector just runs individual min-max queries. You can turn on like the database profiler when you run a job like this, and see the actual like source queries that it's running. But it's trying to run them all in parallel. So it's trying to get as much concurrency out of the system as possible because it is a bottleneck.
So what you just described, is it like a Hadoop Mongo input format that computes input splits?
Yeah. So there's actually there's a class in the connector called like Mongo input splitter. And there's sort of 3 or 4 variations of it depending on whether you want to split by shard. So you can split at this level completely. You can split at the individual chunk level that's in these things. That's for a sharded cluster. For an unsharded collection, you have to basically use the default like split vector mechanism. But then you have to specify how many splits you want, because it'll usually just try to do 1 split per mapper. But in some cases, you might want more splits or less splits depending on what you're trying to do. So you have a little bit of tweaking you can do to find the right balance. A couple things to remember with Hive, though. This is pretty critical. Queries like where predicates are not pushed down to MongoDB. So you may have a create table statement and 1 select statement with a where clause that may filter out half the data. Doesn't matter. We're going to read the entire collection in, and then when it gets into Hive, then we'll cut it loose. So that's a lot of work. So this is actually an area that we're spending a lot of time on right now. The lead developer on the connector is basically working on not predicting, but looking and seeing where predicates are in a file or in a Hive query and saying, all right, well, I could just pick the very first predicate and use that to limit the total amount of data I bring in. So instead of bringing in like a terabyte-sized collection, if you only need 10 gigs of data, just bring in the 10 gigs instead of dragging it all across the wire, because it's a huge performance. It just drags things down. So that's a big optimization that he's working on right now, but we hope to have that out, I think, later this fall at some point. The other big one too is when you do that create table statement. So here, I just ran this by itself. If I run it, and if I hit drop table after this, if I type that in and I run it, it's actually going to drop the Hive table, right, the metadata version, and it's going to drop the source collection. So you have to tell it, you have to tell Hive to use this external flag. So you have to say create external table. And that way, when you drop the table, it's not dropping the source collection, it's just dropping the one that's inside of Hive, like the metadata copy. And I can't tell you, I hit on this because I do this like once a day, where I forget the external flag, I drop a table, I wonder where my data is, and then I have to start all over again. So just remember that. It's pretty useful. All right, so with Spark, you do sort of similar things that you would do with MapReduce in terms of laying out the config and then reading the data in, computing, writing the results back out. But Spark is super optimized for a lot of in-memory usage and cool operations. But you really work with it the same way. So you create the config, you specify the input URI or the BSON file location, and then it reads that data back in using the same APIs. What we're looking at doing in the long run is if we can make, instead of having you go through the typical MapReduce API, using the MongoDB, like we're creating like a MongoDB Spark resilient distributed data set. It's called an RDD in Spark. If we can create classes for that, then we can get a lot more optimization out of parallel reads and parallel writes. right now when you compute with Spark and you want to write results back out to MongoDB, they're basically single-threaded writes. So it takes a long time. So like in the demo that I was going to run but is now broken, I have to write out like 6 million records. Well, it's just running like 5,000 inserts a second, right? It's terrible because only one thread can write back out because of the way the MapReduce API is, right? It's assuming a bunch of reducers, where in this case, Spark has one sort of output filter, but it can parallelize the work, but the way the API works is it can't use it. So that's another area we're trying to optimize because Spark is becoming so powerful that we want to make sure that input and output is equally fast. That was kind of a weird explanation, but it'll make sense later, I promise. If you look at the code for a Spark example, it's pretty basic, right? To read data from MongoDB, you create a new Hadoop configuration object. I set some parameters like the job input format, which is the Mongo input format, the URI, which is the collection database name, and then I just create a Java RDD, which is, Spark is typically written in Scala, but they actually have Python and Java APIs. I use Java because I don't know Scala. So it's a little bit more terse or verbose than a Scala class call would be, but you get the same idea. I just create a new Hadoop-centric data set, and because it knows that it's using MapReduce APIs, it knows how to use those from the connector and just go and pull them out and read it back in. So it does the same parallelizing on read that it does with MapReduce. So the biggest thing, and we already kind of touched upon this a little bit, which is great, is how you get this data in, right? Because ultimately, you want to have the most up-to-date analysis and queries across the data, but you also have to manage the operational impact it puts in your data set. Right? If you're running an application or a series of applications on MongoDB, and you're doing like millions of reads and writes a second, adding in Hadoop jobs into that mix is going to drag things down negatively, right? It's going to impact the system negatively. So you want to manage that impact. So there's no great way to do it right now. It's kind of like a series of trade-offs. Either I do dynamic queries against my source data, which is powerful, but puts load on the system, or I take like snapshots of that data, every night or every hour or something, and I dump it off to the side, put it in HDFS. That's great because I can manage the operational workload of taking a backup snapshot, but it's also not the most recent data anymore. So it ultimately comes down to the question you're asking. I think it's safe to say, like, for recommendation systems, maybe you don't need the most, up to the second data because you could still get a lot of value out of having just good recommendations that are maybe an hour old or a day old. So there's a little bit of a trade-off there. This is like the third major area we're trying to actively figure out the best way to go. There's a lot of crappy solutions, and converging on the right one is kind of hard because you want to have, our dream solution is dynamic queries, most recent data, minimal operational load. So we're trying to, hunt for the mythical unicorn here.
Yeah, what about that sort of real-time?
Yeah, like streaming into the thing. So that's one approach that we talked about.
It's going to be a coffee that's, almost real-time, real-time. So
yeah, it turns out. So that was kind of the road we went down initially. So I don't know how much you guys know about the way MongoDB's replication works, but in a primary, secondary, basically when you write data here, you write it into two spots. You write it to the source database that you're writing to, and then it also gets written to what's called an op log. And that op log is just this it's a collection of just individual operations. Secondaries tail this op log. So when they see an operation come in, they apply it to their version of the data set, and that's how replication works in a very sort of boiled down scenario. We actually initially went down this road of saying, well, can we just read this op log and consume this? It turns out you really can't, because HDFS, while a very powerful distributed file system, it's actually a terrible everyday file system. HDFS is append only, and so the way our operations read out of the op log is there are a series of updates to data. You can't actually update data in HDFS. You write it and you can add to it, but you can't change anything. So it's a lot harder of a problem to solve with that approach. So we're looking at other ways. One is, could you just run MongoDB on HDFS and have it write data there? I tried that actually, and it failed much faster than I thought it would. It broke really quickly, so that one was kind of out the window. So we're still evaluating. There's a couple of other sort of academic options at the moment. They're not at all production ready or worthy yet, but we are very much invested in trying to solve this problem. So what we're kind of thinking now is there might be a way with what's coming in MongoDB 2.8. So one of the things we announced back at MongoDB World in June was pluggable storage engines. So there's possibly a way we could come up with a storage engine that might support HDFS straight from MongoDB, but as you can tell, I kind of couched it about 15 different times because I've seen it work, but I saw it work in the most held together with like sticks and bubble gum kind of way. So we're not really sure if it can scale quite yet, but that's kind of what we're thinking. Because I think that's the best approach, where you just run another secondary here, and that secondary happens to write to HDFS directly. So it's most recent data, and you're not putting any load on the operational side. That's probably the magical best approach, but there are a lot of technical hurdles to get through.
Real-time ETL.
Yeah, it's basically just always there. So now when you want to run up to the second MapReduce job, you just point it to that section on HDFS.
But then you don't need the connector.
You still need the connector for, well, I mean, yes, actually, honestly, that's a good thing, right? We don't want to have an extra mechanism to go through. We prefer you just go straight talk to your data. But the connector is still useful for writing back out to MongoDB, which people want. But also the file format here is not going to be like a text file format. We still need something probably binary encoded in some way so we can get good performance out of it. And so you'll still need some set of libraries to read that data, just not sure what yet. So we're playing with a couple different options. All right, so I had a demo. I'll tell you what the problem is. For any of you guys that sleep wake your machine a lot, I have my Hadoop cluster. When I say cluster, it's like 3 nodes running on my machine right now, but all the host names are set for my work IP address, and when I opened it up here, they broke. So I'll walk you guys through the code. It actually does work, I promise. I'm not making it up. But I did run it earlier today, so I have a backup result, just in case. But basically what I did was, I built a little movie application. There's a data set out there called Movie Lens from the Group Lens machine learning group at the University of Minnesota. It's like 10 million movie ratings, 10,000 movies, 70,000 users. So it gives you a good sense for it. And that's about 70 million ratings in total possible, so they left out 60. So the idea is that I would take 10 million ratings in, read those in, create a collaborative filter. And so basically based on like people who rated similar movies in the same way, or had similar profiles of movies that they rated, I could create a predictive mechanism and say, all right, well, if I like movie X and you like movie X, and we both rate it the same way, then if you like movie Y, I probably will like movie Y the same amount, right? That's sort of a collaborative filter in a nutshell. Compute all that data in Spark, and then pump it back out. Now, the downside is that if I run this with the full data set, it takes like an hour or more, in fact, because it takes a long time to write the data back out. The actual compute is like really short, but the writing out is so slow because of that single-threaded mechanism, and I'm running on a laptop. So I took a smaller data set where I had like, I think 1,000 users and like maybe like 7,000 movies. So it's a little bit smaller, but it still wrote out about 6 million records on the way out. And then I built a simple Python web app to let you browse the movies. And then it, like I said, uses a collaborative filter. And the way it worked is, you know, if I go through, and let me jump out here for a second. I'm going to show you guys what it looks like. Right, so that's the backup one. Okay, yeah. So you can just browse around this like movie web website. We've got things like top movies, right? Some of this came out of the source data set. I'm logged in as user 500 because I made up a user ID mechanism. But if I look at recommendations, right, there are no recommendations, right? Because I don't have anything in here yet. If I look at ratings, I can see a movie that I rated, but there's no recommendations here either. I'm not seeing what else I might like. And so in the sort of working version that I will show you guys now, the same kind of concept. This one just has the data set filled in. So if I look at recommendations now, there it goes. Okay, so now I get recommended movies based on ratings similar from what I've seen. If I go back to my ratings and look at movies that I've rated, I can click on like Dead Man Walking. And then what I basically did to power this was I went back through all the predicted ratings and I said, all right, well, show me the ones that are the top for the first genre that shows up. So I went and found the top rated movies for this user for crime, and I showed them their predictions based on that. So basically it's like saying, you might also like this movie since you liked this one. There's a lot more I could do here, right? This is just a really basic application. But the idea was, can I show this, you know, can you show something like this in practice and how it's actually useful for like a retail use case? Let me walk through the process and then I'll show you guys what the code looks like, because it's pretty amazing how small it was. So yeah, so the application lets you browse by ratings count, by movie count. You could log in and see your own ratings that you've given. But what's missing in the vanilla version is movies you might like and other recommendations. And so that's what the Spark app computes. And so the way I run this is I have Hadoop 2.3 on my system, which is only a few months old, but they're already on 2.4.1. And I use Spark 1.0, which is also 3 months old. I think they're on Spark 1.01 right now. I executed it locally, so I didn't submit it through the normal yarn process because I didn't have that many resources to manage it. There's only one yarn node running, but you can run Spark jobs in a multitude of ways, with or without yarn. And then what I did was I pulled all the data off of backup snapshots from HDFS. So I have BSON files that I put in HDFS. I pulled them off of that, and then actually write the ratings documents back out to MongoDB from the Spark application. So if you look at the way the process kind of goes, like I snapshot the database, I put the BSON in HDFS, BSON gets read into the Spark application, and then I create a model, or I train a model from the existing ratings, like the existing 10 million, and then I create a matrix of all possible user movie pairings, right? So I just basically do like the Cartesian product of all users and all movies, and then I predict the rating. So I go back through that matrix and fill it in with predicted ratings based on the trained model I've got. And then I write those predictions as individual MongoDB documents back out to the running deployment. And then that web app exposes them. And then you can do something like this on a weekly basis, right, where you recompute. What I didn't do in my version was I didn't save the model I computed and then add to it later on. I'm just blowing it away and starting again every time because it's pretty fast over a small data set. But typically what you do is typically what you do is you would persist the core model and then read it back up, like basically deserialize it back into your code, add the new ratings, rerun the training algorithm across the newer section, and then predict again. So there's ways to kind of add, iterative data to it over time. Yeah.
In a commercial app, would you use Spark for your predictive models, or something like SAS or Revolutionary?
I think that's a good question actually, because Spark is not super mature yet, right? It's still relatively new. It's in 1.0 at this point. I'll tell you what, I would invest more in Spark at this point than I would in other things because the ceiling is so much higher, right? We're only beginning, like Spark is only beginning to scratch the surface of how fast and how powerful they can be. And the APIs are there to go as powerful as you want to go, right? Or as complex as you want to make it. So there's so much working functionality that's baked into it right now that I think it's worth investing in it.
So something like R, where you're developing analytical models, is that fit into the place where Spark is right now?
R is good, but not nearly at the scale that Spark can run on. So R is great. Let me walk that back a little bit. R, like the open source R, no way could ever handle this data set size. Well, in this case, yes, but like in the real world, probably not. The R that's coming out of Revolution Computing, those guys are actually trying to get R running at scale, and they've had some success in turning R algorithms into Hadoop jobs, but it's also not a perfect fit because it's still really hard. Doing a logistic regression in MapReduce literally would make you insane. Like I saw someone lose their mind over it because it's really hard to do. So it's hard to take what is basically one line in R and turn it into a series of MapReduce jobs. It's very, very difficult. So they've started to crack that problem a little bit, but it's still, they've got a long way to go. And I think it's generally hard to make that transition. Now, I think there's a better approach with R and Spark because the way Spark's model is, in terms of how it uses memory and serializes objects, matches R's approach a lot more closely. So there's a much clearer path from R to Spark. So I think that there's a way to do it where you might be able to run one day and say, I run R on my machine, it talks to my local data set, it runs great, the algorithm works, let me go run it on the cluster, and you just pick up your R job and run it there. Like then again, it's like another, it's like another Bigfoot or Saskatchewan type situation. It's out there, and it's not totally possible yet, but people are really working hard to get that to happen. But I think, the best organizations that do this kind of stuff, they don't do their data science on their Hadoop platform because it's expensive. It takes a lot of built-in knowledge about how Hadoop works to make it work. You're better off getting your algorithms right in R and Python, getting the flow and the understanding of your data there where it's small and limited, and then trying to run it at scale. And people will rewrite things, but again, Python's a good example. Python actually you can use locally, but does run on top of Spark. So the PySpark project is getting a lot of attention. It's actually, they have kept parity with the rest of the API, and they support it as a first-class option along with Scala and Java. So a lot of your Python knowledge could translate pretty well into Spark knowledge, basically. Yeah, I have a lot of opinions on this subject. All right, so how I execute this job, even though it didn't work, this is how I would have executed it. It's very simple, right? You just use the Spark submit command. It lets you submit applications for running cluster. In this case, I picked local as my cluster because it was just running locally, but if I had access to a yarn deployment with Hadoop, you just put in yarn there. You could actually specify the number of like executors, like workers, versus the number of driver threads that run. You could pick how much memory each one has. So you get a lot of flexibility in how you submit jobs. And this is just the built-in way. You can do this programmatically as well. So all of the functionality is still there, just a little hidden for you. So that's all I have. Before I show this slide, though, I do want to show you guys what the Spark code looks like because it is pretty small. Try to make this much larger. That's not right. All right. Well, I can't make it any bigger.
There's zoom on there on the right corner.
Oh, way up here.
Yeah.
Yeah, it'll just make it full screen.
No.
Oh, not that one.
The other, the little magnifying.
Oh,
It's search.
That's
search. Yeah.
okay.
Yeah, sorry. All right, this is like really small. You can't read it at all. But the net of it is if you look at this, it's basically like 100 lines of code because I got a lot of stuff commented out here that I didn't need that I was just doing for testing. It's 155 lines at this point. This runs a complete collaborative filter. I'm only feeding in like 5 gigs of data and getting out like a 1 gig response. But you can apply this exact same code to like a terabyte size. And if you get the memory settings and the yarn cluster set up correctly, you can efficiently do this in a matter of minutes. And the code really has to look no different, right? The only thing you have to change is your job parameters because the Spark API is really powerful. To train a model, I mean, most of the time I spend, honestly, in this code is reading input data. Like here, I'm still reading input data all through this point. The actual line to train the model is 1 line to train it, and then to predict the new ratings is another line. And so that's all baked in. I was amazed because I've done this with Mahout and MapReduce, and it takes a lot of MapReduce classes and like an Uzi workflow, and it's not fun. It's sort of a terrible experience. This was like a breath of fresh air. I think I wrote this on like an airplane, which was awesome. And then I spend more code writing the data back out.
So why is there so much plumbing on writing in and writing out?
Just because you have to, like, when you read the data in, you actually have to say, all right, well, here's a MongoDB document. I got to turn this into a Spark native data structure. Just mapping it into, like, you know, for when you want to run the predictive, when you want to do like a model training, you have to put it into a special format of user, product, and rating. So I have to read in my documents and turn them into a data structure and then create a list of those. And then like the Cartesian product requires some extra steps. That stuff. So it's really just about, like I said, mostly just mapping the data in. The actual compute part is really short. And if you look at the way, even in the small data set version that I run, it takes about 15 to 20 minutes. 18 of those minutes, of those 20, are spent writing the data back out. The first 2 are just where it reads in the data, it does the computation, and it's just spent time, writing it back out. So it is pretty fast and powerful. Again, even at 1.0.
It's a Spark issue, or
it's a
that you write out serially?
It's more of a connector problem because the connector support for Spark is through the MapReduce API, and the MapReduce API is like, I see one thing at a time, and that's what I see. I can't do things like batched writes. I can't bundle up like 1,000 documents and write them at once. I have to do one document at a time, and there's a lot of like network overhead, even locally, to do that. So that's where we're looking to see if even if we can make like just a small improvement to make that faster, because it's needlessly simplistic. Because again, the MapReduce API, I don't want to knock it. It's still very powerful, but it is simple, and that's the downside.
And Spark's kind of seen as an alternative altogether.
Yeah.
Potentially replacing it completely.
Yes. Definitely an
If
alternative.
you're kind of getting new to big data,
yeah, I would actually.
Feel any advantage in kind of?
No, if I were telling somebody brand new, I was telling a friend this who just finished her PhD, like I would look at Spark, Pig, and Hive. Because if you know Pig and Hive, you can just skip MapReduce entirely. It's good to know how it works and that it does turn it into MapReduce jobs, but that's pretty much the limit of it. And then with Spark, you're going to get any higher level powerful abstraction, like a true machine learning or graph analytical problem, you'll do with Spark anyway, because the APIs are there. And frankly, like I said, with Mahout abandoning their old code and moving to Spark, like everyone is kind of seeing which way the wind is blowing and which way they can, again, where the ceiling is higher for them to go to.
Do you have a sense of the 3 that you mentioned, performance-wise, just like a 1x, 2x difference between them, or?
At this point, so they're not all really for the same thing, but generally speaking, if you were to kind of try to compare apples to apples in most of the cases, Hive is probably the fastest right now because there's so much work into making Hive really, really fast. And then Spark, and then probably Pig last. And that's just by virtue of the way it works. Now Pig is actually also getting better. Like they're trying to optimize, like when you write a Pig script, it actually generates behind the scenes a series of MapReduce jobs, but they're trying not to run them serially. They're trying to create like a directed acyclical graph out of it. So you can actually run different parts of the compute in parallel across a large cluster so that you can converge on the result a little bit faster, but that still is taking time. I think like now they've gotten to a good point with Pig 0.13. So that's pretty good. And then Hive, the versions are problematic because everyone has a different, like Cloudera has Hive 11 with Cloudera fixes, Hortonworks has Hive 11 with their fixes. Hive 12 is basically where they're converging towards. Hive 12 is much faster than Hive 11 was, and it's continuing again to get faster.
Are they standardized on the HQL or HiveQL or whatever?
Yeah, the query language is mostly staying the same for Hive. It's just the internal fixes and optimization they're doing. So, and a lot of the, if you look at the, if you kind of dig into like the fixes that Cloudera and Hortonworks both make, a lot of it's around security, right? They're very security focused. They're trying to add a lot of security to Hadoop because they're seeing, again, like it has a low ceiling in a lab, but if you go into an entire company, it has a much higher potential, but you have to start taking into account things like redacting fields and how to control information flow, who can see what, who can't, because you're giving away a lot of information out there. So let me put that last slide up here so you guys can see if you want to follow up at all. All right, so obviously the connector's out there. It's open source. It's up on GitHub. We just released version 1.3 of the connector. Most of it wasn't anything crazy, just some bug fixes for like CDH5 and Hortonworks 2.1. But the best thing is that you no longer have to build it yourself and include it in your POM file in Maven. It's actually back on Maven Central, so you can refer to the artifacts and get them downloaded automatically. That was a huge complaint I had. There's a getting started guide, which is a little bit out of date, but the idea is still there. If you want to just get started with the connector basics for Pig, Hive, and MapReduce. And then this demo that I was going to run that didn't work, which sucks, is up on GitHub as well on my GitHub repo, which if anybody's interested, I'm happy to talk about that more. So, that's all I've got right now. One more quick thing, we are hiring locally. So if you are interested in either joining our technical services team, which supports a lot of our customers and partners, it's not your typical support channel, right? This is like people who have like really broad distributed systems knowledge or really crazy security knowledge. It's a pretty difficult job, but it's really rewarding. It's awesome to get to work with our customers. We're hiring at least one more person for that locally, and then we're also hiring one more person for our performance team, because we're building a performance team in New York, Palo Alto, and here. And so it's already off and running, but they are knee deep in all kinds of metrics work and performance work for MongoDB 2.8. So yeah, that's pretty much it. Thank you guys for coming.